I'm Zibi Turtle, and I'm in the planetary exploration group in the space exploration sector. And I'm the PI of the Dragonfly mission concept. This is a mission concept that we have proposed to New Frontiers, NASA's New Frontiers program. This is the same program that New Horizons is in, that the Juno mission and the OSIRIS-REx mission that just got to the asteroid Bennu are also in. And a couple of years ago, NASA put out a call for the next mission in this program. And 12 proposals went in April of 2017, one of which was Dragonfly. And we found out a year ago that Dragonfly and one other mission were selected for further study. So a big team of us have spent the last year working to do as much design development as possible in just a year-long period on this mission concept. And in fact, the big tome of the mission study, the concept study, just got delivered to NASA yesterday. So I'm going to talk to you about Titan and the Dragonfly mission concept that we have proposed. So why do we want to go to Titan? Well, Titan, in many ways, is similar to the early Earth. And we don't know the steps that were taken on Earth to get from chemistry to biology. But a lot of that prebiotic chemistry is actually happening on Titan today. There are a lot of places in the solar system that hold the key, different aspects of the keys to the development of life, but Titan is doing these complex organic experiments. And so this is the place that we'd like to go to pick up the results of these experiments. Titan is the largest of Saturn's moons. And you can see here, pictured with its siblings, it's also very different from its siblings because you don't see its surface. And this is because Titan is unique in that it has a thick atmosphere. It's not only unique among the Saturnian system, it's unique with respect to the other large satellites in the solar system. Here's our moon. These are the Galilean satellites with Europa here, which is another target for astrobiology. But again, you can see that Titan stands out very dramatically. And it's actually very unique among the planets in our solar system as well. Its atmosphere is actually the second densest of a planet with a solid surface after Venus. The atmospheric pressure at the surface of Titan is 1.5 bars, so it's actually denser than the atmosphere here on Earth. So Titan is actually slightly larger than our moon. The surface gravity is about 14% of the gravity here on Earth, or almost the gravity on the surface of the moon. So it's got low gravity compared to Earth, but as I said, it's got high surface pressure, a much denser atmosphere, a much more extended atmosphere as well. But out at Titan, the surface temperature is 94 kelvins. So it's a lot colder than it is here, and at these temperatures, the bedrock of Titan is made of water ice. And the atmosphere is also, like our atmosphere, mostly nitrogen. But the condensable species in Titan's atmosphere, unlike water on Earth, is methane. And this is what makes the atmosphere and Titan such a rich place, because that methane is broken down at the top of the atmosphere by photochemistry. And the molecules recombine to make exceedingly complex organic compounds. And that's at the top of the atmosphere. And these materials fall out onto the surface and are then further processed by other interactions. And so these are the types of experiments that we want to understand. So the Cassini-Huygens mission is a joint NASA-ESA mission that explored the Saturnian system from 2004 to 2017, just ended over a year ago. And during the course of that mission, there were 126, the Cassini orbiter made 126 close flybys of Saturn's moon Titan and mapped out the distribution of materials on the surface, the distribution of landforms, the geography of Titan. So we can see here in this map, in the near infrared, about 938 nanometers, that there's a wide diversity of features on the surface of Titan. But what we don't know is the detailed composition. We know there's rich organic material all over the surface, but we don't know the detailed composition of the different types of landforms. The Cassini orbiter carried with it the Huygens probe built by ESA, and it actually was designed to measure the atmosphere as it descended down through the atmosphere. And it survived to land on the surface. And here's a picture from the surface of Titan. So we have a little bit of atmospheric truth and ground truth of Titan from the Huygens probe, but it was designed for a very short mission, just a few hours on the surface. We know that Titan's surface is very rich. It has a wide variety of landforms, very much like Earth. We have impact craters. There may be cryovolcanoes, cold volcanoes, of which the lava would be liquid water. There are dunes made of organic material, as opposed to the silica sand we think of for sand dunes on Earth. And there are even rivers and lakes and seas of liquid hydrocarbons. So it's actually an incredibly Earth-like place, except that the materials undergoing the same kind of geologic processes are completely different from the materials here on Earth at these cold temperatures. And beneath the surface, Titan has a thick liquid water ocean. So as many of the satellites in the outer solar system, Titan is an ocean world. And this is the level of chemistry that Titan supports. So for each of these dials, on the left is a comparison of the heaviest or the most complex carbon-bearing molecule on that world. And on the right is the amount of carbon on the world in the atmosphere and the surface. So you can see, compared to to other bodies in the solar system, while some, like the gas giant Saturn or Venus, have a lot more carbon, the complexity of the carbon on Titan is really can really only compare to the complexity on Earth. And so this, again, is why we want to be able to go to Titan. Because it gives us it allows us to take the next steps to understand what makes a world habitable and what the chemical processes are that led to the development of life. So we know that Titan has all the key ingredients necessary for the development of life. It has energy in the form of sunlight that drives photochemistry in the atmosphere. It has abundant complex organics because of this chemistry in the atmosphere and interactions on the surface. And then it has liquids. But it has two kinds of solvents. So not only are there liquid hydrocarbons on the surface, which could act as solvents in an alternative, exotic biological system, but there will also have been liquid water present on the surface in the past, and there is liquid water in the interior ocean. The water on the surface could have come from cryovolcanic eruptions of liquid from the interior to the surface, or also in the form of impacts, which will melt the target water ice and result in large pools of, or large reservoirs of liquid water for tens of thousands of years. So it's really an ocean world laboratory that has been doing these organic chemistry experiments for hundreds of millions of years. And what we want to do is to be able to get to different places on the surface, to be able to understand the different chemistry in different environments. We know from Cassini-Huygens, this is a near-infrared map of different types of materials on the surface with a representative color so that you can really pull out the variety of materials. We know where to look for the answers to these fundamental questions on the surface of Titan. The challenge is to get a capable instrument suite to multiple locations so that we can sample material in situ in different environments to measure its composition. So the mobility is key. And that's why we proposed Dragonfly. So Dragonfly takes advantage of Titan's atmosphere, the thick atmosphere, the low gravity. And it's strictly an octocopter. We sometimes call it a dual quadcopter because it's got two sets of 4 rotors. And this allows us to take the entire suite of instruments from place to place on Titan. When we land, you'll see here the high-gain antenna deploys. We're able to communicate directly from the surface of Titan to Earth. So that simplifies the mission. That means that we only have the single unit, and we can take the power source, the MMRTG power source, which you can see here, with us, and the instrument suite with us from place to explore Titan. So we'd be able to pursue in situ operational strategies very similar to the rovers on Mars, except that we have a much more relaxed timescale, because Titan's day is 16 days long. So no one has to live on Mars time or Titan time. We have a lot more time to be able to interact with the lander. And we would perform most of the science activities on the ground. In fact, most of the time is spent on the ground, with flight used for relocation in between science activities. And we can make some measurements in flight as well. The flight uses battery power, which is charged by the MMRTG between flights. And again, we have ample time between flights to be able to do that. So this combines previous exploration strategies in a new and unique way. It's certainly not the first time anyone's thought about exploring Titan by air. We've had concepts from helicopters to balloons to airplanes. All of these have been considered. And in fact, many of the flagship mission studies of Titan combine different elements. But what we've been able to do with Dragonfly is combine these elements into a single New Frontiers mission, because we have landed and aerial capability. So we can accomplish the wide variety of science objectives important to the planetary decadal survey. As I said, flight is easier on Titan than Earth because of the atmosphere density and because of the low gravity. Heavier than air mobility is very efficient. It's actually easier to fly on Titan than it is on Earth. If you had wings, you'd be able to fly on Titan, which makes it a pretty cool place to be able to explore. And the regime in which the Dragonfly rotors would function is actually a very well understood regime, and one that is very straightforward to test on Earth, which leads to means we can do a lot of the testing of the system before we launch it. And of course, there's been a huge explosion in the use of drones and autonomy for flight. And so we really can leverage all of that development in the last couple of decades to apply it to Titan. We'd be able to do multidisciplinary science measurements at dozens of different landing sites, traveling tens to hundreds of kilometers across the surface. The focus, of course, is the prebiotic chemistry and habitability. To do this, we need to be able to analyze the chemical components, processes at work on Titan in great detail. But to do that, you also need to understand the results of that, you need to know the context. So we would also measure atmospheric conditions. We would constrain processes that mix the organics together and mix them with past surface liquid environments. And because we have the capability to search for detailed chemical compositions, we also bring with us the ability to search for chemical evidence of water-based or even hydrocarbon-based life, were the chemistry on Titan to have taken that step from chemistry to biology. So the payload consists of a mass spectrometer. We call this DRAMS, the Dragonfly Mass Spectrometer. So it'd be built by Goddard based on the SAM and MoMA instruments that are, one of which is on Mars and the other is designed for Mars. This allows us to do very detailed chemical measurements of the surface composition. And if, as I said, if chemistry has taken the step toward biology, we can actually distinguish between abiotic and biotic processes that might be going on, or the results of those processes. We'd also carry a gamma ray and neutron spectrometer. This allows us to measure the bulk elemental surface composition, to classify the material very quickly on the surface, to make decisions about what kind of sampling we would do, what kind of measurements we do with the samples. So this instrument is based on the GRNS that Messenger carried, as well as the instrument being built for Psyche. The real difference is that for Titan, because we have an atmosphere, we don't have cosmic rays hitting the surface, so we also have to bring with us a neutron generator. Then there's an instrument that will do meteorology and geophysical measurements. This allows us to monitor atmospheric pressure, temperature, wind, humidity, to understand the context in which we are making the measurements of the surface materials. We'll be able to measure thermal properties of the surface as well, and we'll bring a seismometer so that we can listen for Titan quakes, to understand the seismic activity of Titan and potentially constrain the thickness of the crust separating the surface from the deep interior water ocean. And with the atmospheric monitoring instruments, we can also make measurements in flight. So we can do atmospheric profiles as well as making measurements of diurnal and spatial variability from the surface. And then we'll have a suite of cameras ranging from microscopic cameras that will focus in on the area that we sample to be able to take very high resolution images of the material sampled, all the way up to cameras that we will be able to use to take panorama images. And so we've mounted cameras here on the high gain antenna, which is articulated, and that allows us to build up a view of the entire area around the lander. And then we have cameras as well that look down and look ahead, and these allow us to do aerial imaging in flight, which not only is important for understanding the geologic context of the area we're in, the areas we're exploring, but allows us to scout all of our landing sites in advance. So the plan in the New Frontiers program is that we would launch in 2025 and arrive at Titan in 2034. This is actually really good timing because 2034 is basically a Titan year after the Huygens probe descended. So we have atmospheric truth. We know what the atmosphere of Titan was like at that time of its year. And we would land at a very similar latitude as well. So we have information from Cassini-Huygens to understand the atmosphere and the area that we'd be landing in. And what we would do is actually land in, this is a radar image of Titan. We would land in an interdune area within the equatorial sand seas on Titan. These are not Titan, these are Earth. This is the Namib Desert. And you can see here the broad, flat interdune areas, which allow a very safe, well-characterized landing area, but also allow access to two types of material within very close proximity. So scientifically, it's a very valuable site, especially since sand dunes tend to collect material from broad areas. And so we expect that that's the case on Titan as well. We would explore Titan for over 2 years, covering a variety of terrains up to hundreds of kilometers apart. And we'd use this leapfrog strategy to explore, which means that from any given site, when we're flying from site A to site B, we would actually overfly another site to scout it out, which means that we know what territory we'd be heading for. It'd give the science team a whole lot of things to argue about where we want to land and what kind of measurements we want to make. But it gives us the chance to scout all the sites before we get to each site. All right, so this is a flight demo we did last May. This is about a half-scale model. And this is built by one of our partners, the team at Penn State University. You'll see a pilot in the video here. The pilot is just there for safety. This is actually a fully autonomous flight. You actually also kind of hear in the background the wind. This was a very windy day. Not actually that windy for Earth, but very windy compared to Titan. But nonetheless, the stability of the rotorcraft, even at this scale and in this wind, was great to see. So like I said, we can do a lot of this testing here on Earth as well directly, and we've already started that program. So this allows us to explore Titan fully, to really comprehensively understand its chemistry and how the compounds on the surface have interacted in different areas on the surface, different environments where we know there's been liquid water, for example, or water ice material, as well as the organic material. And this will allow us to explore the habitability of an alien environment and an ocean world in a truly revolutionary way. The next steps, I said that the concept study report went in yesterday. The next step is that we will have a site visit in March here at APL. And then NASA will be deciding what mission they want to fly sometime later in 2019, and we hope that we will literally be able to fly on Titan as a result. Thank you.